Hello my dear students. In this lecture we will continue with the dynamics of electric drives. So, the criteria for steady state stability. So let the equilibrium of the torques at the speed is tau m, tau l, omega. So it is actually represented like this: tau m, tau l and omega. And the small deviation, suppose there is a disturbance. So due to the disturbance, what will happen? The motor torque will change, the load torque will change, and the speed will change. And let us assume that the deviation is very small. So the change in the motor torque is given by delta tau m. The deviation in the load torque is given by delta tau l, and the deviation in speed is given by delta omega. So now, if we assume that the fundamental torque equation is this, so let us replace the terms over here. So the parent equation will be, I will write it over here, tau m plus delta tau m. This is the new motor torque, right? It is equal to the new load torque. What will be the new load torque? It will be tau l plus delta tau l plus j d dt of omega plus delta omega. So this will be your new load torque equation. So now this is the exact equation that we have written. So now if we change the sides and if we separate the terms, we will get this equation. So there will be 6 terms, but from the fundamental torque equation, this is equal to 0. J d omega dt plus tau l minus tau m, that is equal to 0. So this and this, they will cancel out, and what we are left with, j d delta omega dt, that means this one, plus delta tau l minus delta tau m. That means the incremental changes, this is very important, the incremental changes in motor torque, load torque and speed, they will also satisfy the fundamental torque equation. Now considering the small deviation changes can be expressed as a linear function of change in speed from the torque equation, where all the quantities are expressed in terms of their deviations from the equilibrium. So these are the small deviations. They are expressed in linear function of the change in speed. So now this incremental motor torque, that means delta tau m, and this incremental load torque, that is delta tau l, we can write it as dtm by d omega into delta omega, or delta tau l is equal to dt tau l delta omega by d omega. This is applicable if the change is incremental. So now if we substitute in that equation, we will get this. So this is a first order differential equation. What we will do is we will substitute this in the above equation, that means this equation. So you substitute the value of delta tau m over here, and this delta tau L over here, and if we simplify, we will get this first order differential equation, that is delta omega. So now we can solve this first order differential equation, and we can solve the value of delta omega. So delta omega is equal to delta omega 0, that means the initial change in speed. It is equal to e to the power minus 1 by j into dtl d omega minus dtm d omega into t. So this entire terminology is in the exponent, e to the power minus this entire term. So that means I can say delta omega is equal to delta omega 0 e to the power minus some kt. That means if t tends to infinity, what will happen? This delta omega will be tending to 0. That means for very long time, or for after some time, this change in omega, that means delta omega, that will disappear in the system. That means the change in speed in the system, that will disappear after quite some time. So that means the system will become, or the system will attain stability. So now the notations are given over here. So delta omega 0 is the initial value of the deviation in speed. So for the stable system, the exponent must be negative. So speed increment will disappear with time. The exponent will always be negative if this is greater than 0. That means this thing, this delta or dtl d omega minus dtm by d omega greater than 0. So this is the condition of the stability in the system. So what does it imply? So this is very important. So the criteria for steady state stability is for a decrease in speed, the motor must, so for the decrease in speed, the motor must exceed the load torque. So for decrease in speed, the motor torque must be greater than the load torque, and for increase in speed, the motor torque must be less than load torque. So this is 1, this is very important, and this is 2. So these are very two important deductions that is obtained from this equation. So you see, when the change is negative, that means when there is a deceleration, as point number 1 is given. So what will happen? What should the motor do? The motor should accelerate and compensate with the falling of the speed. So that's why tau m should be greater than tau L. And as point number 2, when there is a disturbance in the system which is accelerating the rotor, that means plus delta omega, so the motor torque becomes lower, so that the speed of the system will reduce to that extent and it will be compensated. So the load torque tau L results in equilibrium point, and the tau L double dash results in the unstable situation. So these point, they will be observed in the next figure. So it will be explained in the next figure. So let us see this. So now suppose the motor torque tau m is denoted by this line, and suppose the load torque, you forget tau L double dash. Let us assume that this is the tau L dash, and the operating point is this one. So we are concerned with the lines marked with red. So this is your operating point. So let this be the speed or the operating speed. Now suppose there is a sudden reduction in speed. So now let us see that there is a sudden decrease in speed. So the speed reduces to omega 1. So what will be our observation? How will we determine whether this load torque and this motor torque, that will be stable or unstable under the circumstances if the speed is reduced? So now suppose your speed has reduced to omega 1. So what will be the point of intersection? So omega 1 intersects tau L dash in this particular point. Let that be point be A, and the speed omega 1 that is intersecting tau m at this particular point, say this is B. So at point A and point B, which is greater? For omega 1, which is greater, the load torque or the motor torque? Obviously here tau m is greater than tau L. And what about the speed? So delta omega here is negative because the speed has reduced. There is a negative acceleration. So obviously if there is a negative acceleration, the motor torque should increase the load torque, and exactly it is happening over here. So the system is stable. Now let us assume a second case. Instead of reducing, the speed is suddenly increased over here. Say it increases to omega 2. So you see omega 2 intersects the tau L at point D and tau m at point C. So now which is greater, tau L or tau m? So here tau m is less than tau L. And what about the acceleration? So acceleration is positive. So the change in speed in positive. So it is plus delta omega. That means accelerating. So obviously if there is a sudden disturbance which is causing acceleration, so what should the motor do? The motor should slow down. So the motor torque should be less than the load torque. So for this case, this is also stable. So the operation is stable in this regard, whether the motor accelerates or decelerates. So now let us assume the graph tau L double dash. Again, let us say the operating point is here, and this point is nothing but omega. Now there is now we will be focusing on this graph and this graph. Now we will forget tau L dash. We will be focused with the new load torque tau L double dash. So now what happens? Omega is suddenly reduced. to omega 1. So you see here, omega 1 intersects tau m at this particular point. Say this is point A, and omega 1 intersects tau l at this particular point. So this point is B. So which is greater, tau m or tau l? So here tau m is greater than tau l. And what is happening? It is delta omega is minus. So you see, the disturbance is causing a reduction in speed. The disturbance is making a reduction in speed. So here, sorry, I made a mistake. This should be tau m less than tau l. So if you see the intersection, tau m is lesser than tau l. So if you see the torque here, this is tau m and this is tau l. So tau m is lesser than tau l. So for the negative acceleration, because speed is reducing, tau m is less than tau l. That means the disturbance is causing a system slowdown or reduction in speed. Now tau m is also less than tau l. That means if tau m is less than tau l, what will happen? The speed will reduce even further and the system will collapse and the motor will slow down to 0. So this is unstable. This is an unstable system. So on the contrary, again we will highlight these torques in red, and let us now assume your operating point is this one, omega, the point of intersection of tau l double dash and tau m. Now previously there was a deceleration and now there is an acceleration. So now here you see what is happening. There is an acceleration to omega 2. So now omega 2 is intersecting tau l over here. So let us redraw this once more. The intersection, if there is an acceleration, suppose the intersection is over here. Like this. So now if there is an acceleration where the speed increases to omega 2 from this point, that is omega 1, so this is tau m, this is tau l. So you see here tau m so here I will draw it like rather this, it will be better. Now the intersection is only at tau m. for an increase in speed from here. So this is omega, this is omega 1. That means we are not getting any tau L intersection. So that means automatically the system will collapse, because the operating speed should intersect both the motor torque and the load torque. So here also the system will be unstable. So we will stop over here. This is all about stability. And you see, before going, so these are the important points. To check the stability of an operating point of the motor, if an increase in speed is greater, the increase in load torque than the motor torque, the speed will tend to decrease and return to its original value. So the operating point will be stable point, else the operating point will be unstable point. This is exactly what we have derived. So these are the different load torque, motor torque profile. So this is left as an assignment to you, where you will analyze the stability of the motor load system for this type of profile. So today we will stop over here finally. Thank you.